Hey, it's Mr. K doing a video for AP Physics 1, and we're going to talk torque. If you are from Physics C, this would apply to you as well. Let's just talk about what torque is. Torque is going to be a lot like force. Force is going to cause accelerations. So an unbalanced force, anyway, will cause acceleration. So F equals ma. So if you have an unbalanced force, you definitely have an acceleration, but it depends upon the mass you're applying that force to and how much unbalanced force there is for that mass. Torque is the same way, but it's going to be rotational. And so the saying is like torque is basically the analog of force, but we're talking about rotation. So with torque, you will cause an acceleration, but it's going to be based upon the object's inertia, which is a lot like the mass, but you care about where the mass is placed. So position matters then, and it'll give you some kind of angular acceleration, or alpha. So just as a starting example, we have, let's say this is a door. So we're looking kind of top down on the door. This is the hinge. These are the handles of the door, so I'd pull it or I'd push it to open it, and it would rotate like this. And so to open the door, you could either push at this location, or you can pull at this location, or you can push at this location or pull at this location. It really doesn't matter. So let's just say that initially we want to give this door a push or a pull in this direction, and that this force is going to be about 50 newtons. Okay, and so we say, all right, we apply this force at this distance away from the hinge, and of course this door will rotate, this door will open, and it will accelerate because we have this force here. And what we really need to talk about is torque. So the other thing that we need to look at is that, yeah, torque, an unbalanced torque is I alpha, but the way you get torque is by applying forces. And you apply forces at some distance away from a center of rotation, and those two things must be perpendicular. So looking, here's my center of rotation, here's my force, it is perpendicular to this distance, and let's just call this distance, about 1.5 or, yeah, maybe 1 meter. And so this whole thing is going to be 1 meter. And so for this current system, we have a torque, a sum of all torque, of the force, 50, at 1 meter away. And that's going to cause some kind of acceleration based upon the inertia, I. So I'll put the alpha there. Okay? And the units for torque, it's kind of weird. But the units for torque, this is I alpha, are the Newton meter. We kind of know that as the joule, but really here it's not joules yet because the torque would have to go through a theta to give you joules. And so right now we'll just call this Newton meters. We would not call that joules. Okay, I know that has the same unit. It's kind of weird, but it has not actually had the time or the distance to really give it energy. This is just like force. If you just have a force, great, but you need to actually have that force applied for a distance or a time to give it energy or momentum. And in the background, Peeves is playing with her ball. Okay, so let's say here we have this torque. It's great. The inertia of this thing, well, the inertia is going to be mr squared for a point mass, but this is not a point mass. This is many point masses. Turns out it's actually about 1/3 mr squared for this solid rod being rotated by its end. As we learn about different shapes, we're going to have different equations for inertia, but they're all going to have mr squared in it, or ml squared. And so r is basically the length of the door, m is going to be the mass of the door. Let's call the mass of the door like, I don't know, 10 kilograms or something like that. And so if we were to say, hey, that's 50 for the torque, 50 times 1, Newton meters is equal to I, 1/3, m the mass of it, 10, r the length of it, 1, square it, we could then find alpha, how fast that door accelerates if we kept on pushing at that rate. So 50 times 3, 150, divided by 10, 15. 15 is equal to 1 squared. That's just going to be alpha then on the right side. And that's going to be 15, I guess I'll write on this side, radians per second squared. And that's pretty high, honestly. So you can find the acceleration. Once you find the acceleration, you can run it through and say, all right, well, what if we want to find the final velocity? It's based on the initial velocity plus the acceleration for the period of time. You can do that. You can find the final velocity squared equals the initial velocity squared plus 2 times the acceleration times the change in theta, not distance but theta. And you can also talk about the change in position is equal to the initial velocity for the time plus 1/2 alpha t squared. So the same kinematic equations apply once you run through the analog of torque, which is well, other way around, the analog of force, which is torque, to get the acceleration. Okay? So what if we were to take that same scenario and to, let's say we instead applied forces at weird spots, and we're going to see what we get. So we have this object. We already know how long it is. It's 1 meter. And we know that the handles are right here. But let's say that we didn't apply 50 newtons, because apparently 50 newtons is a lot. The mass, 10 kilograms still, 1 meter in distance here. So let's say we did this. You came over and you had somebody apply a force like this. Okay? And let's say we applied that same 50 newton force. Would that open the door the other way? Would it be as fast as what we found out here, the 15 radians per second squared? And you're probably going to guess, nah, probably not, because you're not using all the force to do the rotation, you're using a part of it. And so what you would have to do is you would have to find out what the component was that was actually going to be perpendicular to the distance to provide the torque. Okay? And so what if you came in and you pushed like this on the door? I don't know who would do this, but let's say you came in and you pushed like that with 50 newtons. Would that open the door at all? And of course, no, it wouldn't. But would it apply force to the door? Sure. This hinge would have to fight back that 50 newtons to fight the pushing of it into itself. Okay, what if you applied the 50 newtons here? What if you applied it here? Well, would that be as effective as applying the 50 newtons on the outside? And the answer would be, well, no, because your distance is much shorter to your point of rotation, and that would result in less torque. Okay, so looking at these forces, if we were to consider what was, torquing this door or turning this door about this hinge, then we would say, all right, the sum of all torque in this situation is going to be this 50 at a position of 0.5, because that's like halfway. It's about halfway. And I guess we're gonna call clockwise to be positive, since I just wrote that. Going the other way, we would have this other 50, but we would have to multiply that, and let's say we knew, what would we know? We would know either like this angle. So if we knew this angle, we're looking for this side of the triangle, so that's going to be the opposite side, so that would be 50 times the sine of whatever that theta is. And we need to multiply it by the distance of 1 to get torque out of it. And I wouldn't have to worry about this one, because that's providing no torque whatsoever. It's actually it's useless for torque, but it is very useful for our sum of all forces. So whatever this angle might be, I would have to take 50 times 0.5, that would be 25. I would have to subtract 50 times the sine of whatever the angle is. Let's just make it 60. I know we can probably find out exactly what it is because I have graph paper, but whatever. So sine is 60, and what is that, 0.866, I believe? Let me grab this guy. Let's go to degrees, 25, oops, 25 minus 50, the sine of 60. And yeah, I get negative 18.3 Newton meters for the torque on this thing. Okay, 50 sine of 60. Yeah, so we got a good portion of that actually providing torque. It's going to beat out the 25 Newton meters from the middle force. So which way do we rotate? Negative 18.3, we called this way to be positive, so we're actually going to rotate this way. And if my torque is negative 18.3 Newton meters, that's again equal to I alpha. So I alpha would be I 1/3 m, the whole length, 1 squared, times alpha. And so that would provide for me 18.3 times 3 over 10. and that will give me 5.49, it'll be negative still, radians per second squared for my angular acceleration for this case. So we have two forces that are fighting each other. We don't get as much acceleration as we would before, and that should work out. So torque is a lot like force, but it is a rotational analog of force, and not only does the distance matter, but also how much. So do consider that. If you applied a torque for a period of time, or let's go back to force. What if you applied force for a period of time? Well, that's called impulse, and impulse changes momentum. Well, torque for a period of time would change what we call angular momentum. Different letter. Okay. Going on, torque for a theta, for a distance, force for a distance would give us a change in kinetic energy. We call this work. Torque for a theta would give us a change in rotational kinetic energy. Okay, so it's very much the same thing as what we had before, but we're just considering things that rotate. There you go.